USB. Yes. He asked me whether I wanted to dim the lights, and I said yes, and now it's putting them back on.
It's like cropped in. So if I go past 720p, it just crops the resolution. That's so fast. I actually didn't remove emoji support, so I don't know what happened there. That's interesting. I think Discord changed something with their APIs. Yep. It just crashed. What do you mean by crash? It's not loading? Is it working for you? I think it's fine. Try delete your cookies for the website. All right. I think we should get started. So welcome back from week 6. So as promised, assignment 2 is coming out very, very soon. We're hoping to release it by the end of the day, so hopefully by like 10 p.m. or so, you will see an assignment pop up. Maybe I should spoil what the assignment is. Since you've rocked up to the lecture, you get a sneak peek of what the assignment is. So our assignment is related to files. What we're going to be building is a file transfer program. So you might have heard of the utility rsync before. Let's pull up man rsync. Rsync is, whoops, let's do that again. Rsync is a fast, versatile, remote, and local file copying tool. So it's a method that, it's a utility that lets you transfer files across a network or even just between different directories on the same computer. And rsync is kind of special. What it does is instead of copying the whole file, let's say that you've already transferred the file before to a computer, right? If you've already transferred the file, it's kind of like very inefficient to transfer the file again if you've only transfer the entire file again if you've only made a tiny change. So what rsync does is it only transfers the parts of the file that you've it only transfers the parts of the file that you've changed instead of transferring the entire file. And that saves time, that saves network bandwidth, and that's the sort of thing that you'll be implementing in the assignment. So I think tomorrow afternoon, Xavier and I will upload a kind of overview video going through the assignment, but you should see the assignment specification pop up on the course homepage later today. All right, also just make sure people at the back, can you hear me fine? Cool, okay. So so during the last lecture, what did we talk about? We went through the basic file I/O system calls. So we talked about how the Unix file model involves opening a file before we can interact with it. So opening a file gives us a file descriptor, and a file descriptor is really just an entry into a massive array. And we can use that file descriptor to refer to a file, whether we want to read from that file, whether we want to write to the file, etc. We also talked about closing files. So once we're done with the file, we need to close the file descriptor. But we also talked about how writing code using these system calls is kind of brittle. Because when you write code, you want your code to work on as many operating systems as possible. You want your code to work on as many devices as possible. So we don't want to directly rely on system calls, because system calls are dependent on the particular operating system and the particular architecture that you're working with. So C provides us with a bunch of wrappers around these functions so that we can C provides us with a bunch of wrappers around these system calls so that we can interact with files. So we talked about standard io.h. We have a bunch of different library calls inside standard io.h, which kind of wrap around each of those system calls that we talked about. So we spoke about fopen. Fopen allows us to open a file given a path name. We can specify how we want to open that file, whether we want to read that file, whether we want to write to that file, whether we want to append onto the end of the file. There are a bunch of different options, and we can always find out what different options we have with basically any C library function by using man pages. And once again, I'm going to say that it's imperative that you get familiar with working with man pages, because again, we have a closed book exam at the end of term. And in that closed book exam, the main resource that you're going to have access to is your man pages. So if you forget how to use the library function, you want to know how to use man pages to learn more about it. So what different modes do we have for fopen? We have these different 6 modes, and depending on how you want to be interacting with the file and where you want to be inserting new content into the file, then you're going to choose one of these 6 modes. What else did we talk about? We haven't really talked about fclose. I'm going to come back to fclose because fclose does some special stuff as well. But we also have a bunch of different ways to read and write to a file. So we talked about the read and write system calls and how the read and write system calls allow us to write essentially an array of bytes to a file or read an array of bytes from a file. And we have fread and fwrite. So fread and fwrite are kind of like direct wrappers of the read and write system calls. Instead of taking in a file descriptor, however, they take in a file star stream, which fopen gives us back. We've also talked about other library functions, which are essentially wrappers around read and write. So we talked about fgetC, which gets us a single character. It's just like getchar, which we've seen in 1511 to get a single character. fgetC, instead of reading that character in from standard in, grabs that character from whatever file descriptor that you specify. We talked about fputC. fputC is like putchar, but instead of writing a character to standard output, fputC lets us write a character to any given file. All right. So one thing that's worth noting is that we have fputs. fputs gives us a mechanism to write a string out to a file. So fputs is kind of like saying printf%s in a sense. fputs allows us to write a string out to some form of file. So how does this kind of differ from fread? What's the difference between fputs and fread? Well, let's take a look at the arguments that we passed into fread. Sorry, not fread, fwrite. Let's compare the arguments that we passed into fputs and fwrite. With fwrite, we can pass in a pointer to some array. Whereas with fputs, we know that whatever array we pass in is explicitly a character array. So we know that it's explicitly a string. So fputs expects a string, whereas fwrite expects any regular array. So what makes a string special? What do we know about a string that makes it different to any other array? What is special about a string? Null terminator. So we know that a string has a null terminator on the end. And if we look at f put s, unlike fwrite, f put s doesn't take in a size, because f put s doesn't need the size because it relies on the string that you pass in being null terminated. So when it reaches the null terminator, it knows that there's nothing left to write. Whereas with fwrite, we can write any regular array. So it doesn't necessarily have to be a string. It can be any array. There's no guarantee that the array is null terminated, right? And since pointers in C don't really keep track of the size of the data structure that it points to, we also need to pass in the size of that array. So fwrite lets you write any regular array or any buffer of bytes to a file. F put s we should only be using for strings that we know are null terminated. OK, what have we got? F put s, f get s. Yeah. So the other catch is, let's say that you're trying to read from a file, and that file contains a bunch of null terminators within it. So typically speaking, when we deal with text files, when we've been writing code, code files are usually just ASCII files that don't contain random null terminators in the middle of them. But there are other file formats, let's say a PNG. A PNG might have a null byte within it. So let's say that I'm trying to read in a bunch of bytes in from a PNG file, and that PNG file has a null byte in the middle. If I were to use fgetS, well, fgetS is going to try read in a string from a file. It's not just going to try read in bytes. It's going to read in those bytes until it hits a null terminator. So when it hits a null terminator, it says, OK, that's the end of a string. So fgetS will keep fgetS will keep reading until it hits a new line or a null terminator, which is a problem because if you've just got a regular PNG file, which isn't meant to be interpreted as text, it's going to hit that new line, it's going to hit that null terminator, it's going to stop reading. So fgetS is appropriate when we know that we're dealing with like text, so whether it's ASCII or Unicode text, which is a spoiler for Thursday. So fgetS, totally fine if you're dealing with a text file, but let's say that you're dealing with a special file format, for example, a PNG, or for example, the types of files that you'll be working with in the assignment. You don't want to be using fgetS for that. You want to be using something like fread, or you can use fgetC. So fgetC to get characters one by one in a loop, or fread to get a bunch of bytes from a file. OK, so you've got a couple of different library calls in C to read and write from files. Which one you use is really going to depend on context. And in next week's lab exercise, we're going to get you familiar with a bunch of different versions of these, just so that you know what context you should use the appropriate library function in. OK. So one more thing to note is I talked about how we've used getchar and putchar. So you've probably seen getchar and putchar in 1511. You would have seen it in the week 1 labs. Whoops, this is falling again. So getchar and putchar aren't really special. Getchar and putchar are still just using the same read and write system calls behind the scenes. There's no special system calls to like write to your terminal or read from your terminal. It's just using the same read and write system calls to interact with your terminal. So it turns out that your terminal is really just controlled by a file behind the scenes, which we'll see shortly. So read and write system calls we can interact with the terminal by using read and write system calls. Getchar and putchar are special wrappers around these system calls which write to the which read from the stdin file or write to the stdout file. So every C program that you've written have secretly had like 3 files already open for you. There's always been a file called stdin that's been open. There's always been a file called stdout that's been open for you. And there's always been a std error. So if you want to write to your terminal, you can use any of these functions and specify, for example, you can specify stdout as your stream, or if you want to read from your terminal, you can use stdin as your stream. OK. Let's see, what do we want to look at here? OK, maybe this is a good opportunity to talk about these different functions. So actually, should I do this? Yeah, let's do this one. No, we've already done that. let's talk about implementing our own version of the copy program. So let's say that we want to copy a file. I think this is it, copy fgetc. So there's a couple of ways that we can now go ahead and copy a file. So we've talked about using system calls directly. So I think this example over here, we directly invoked the read and write system. Sorry, we directly opened a brand new file. We read in bytes from the original file using the read system call. In this case, we read them in chunks of 4096 bytes. And every time we read in a chunk of 4096 bytes, we used a write system call. We used a write system call to write that out to the file, to our brand new file. We can also achieve the same thing with, can we fread into stodout? You could try use fread on stodout, but you wouldn't get anything because there's no, there's nothing to be read from. Sorry, there's nothing there to read from stodout, my bad. Okay, so this is an implementation of the same program that we wrote using system calls in week 5. But instead of using system calls, we're now using these new library functions. So we can use fputc. Oh, that's the wrong program. OK, let's write this from scratch. I think I meant to write this from scratch. Let's see, cp.io.h. All right, so we want to copy a file. So when we want to copy a file, we know that the CP program takes in 2 arguments. We know that CP takes in a source file and it takes in a destination file. So let's include stdio.h, and let's write up a main function. In our main function, we want to take in command line arguments. So we'll take in an argc, take in an argv. Actually, let's do it this way. There we go. So whenever you write a program that's relying on command line arguments, you always want to make sure that your user has actually given you the right amount of arguments. So there's no point like trying to access an argv1 or argv2 if the user hasn't given us an argv1 or an argv2. That would probably lead to some form of memory issue, some form of memory error. So you always want to be checking that you've got the right amount of arguments. So my program is going to take in 2 arguments. It's going to take in the source file and the destination file. But we also know that argc always includes the name of the program. So in this case, we want to make sure that argc is equal to 3. If argc is not equal to 3, they haven't given us the right amount of arguments. So we'll give them a useful error message telling them how to use the program. So source file, whoops. Are those Discord pings? Oh, it's from here. OK. Destination file. All right, so we've prompted the user to give us a source file and a destination file. Lovely. OK. So now that we've got a source file and a destination file provided by the user, we can try open each of those files. So with the source file, we're not trying to write from it. We're only trying to read the content of the source file so that we can copy it over. So in this case, we know that we can take the source file and use fopen and specify that we want to read from it. So where's our source file? We know that our source file is this first argument. It's going to live inside argv1. argv1. And we want to read from it. Now, let's go back to here. Can anyone spot the issue here? What have I missed? What's missing from this line of code? In fact, let's try run it. It's missing an else. Yeah, I guess an else is one way of doing it. In the case that the user's like not provided the right amount of arguments, you probably don't want to do anything else. So you could just immediately return 1 to say that some form of error has occurred. But there is something else that's missing here. In fact, let's just try run this program and see what happens. Why is this .h? That should be a .c file. OK, let's try compile that. All right, there we go. So it's printed out some random garbage here. So I try to print out a string, but I didn't specify what string I wanted to print out. So it's given me some random output because how printf works is it kind of looks at like your stack to figure out what to try print. And if you don't place anything on the stack for it to try print, it's not going to be happy. So we'll specify that we want to print out v0 there. Try that again, and that's much better. OK. So we've opened up our source file. We also need to open up a destination file to write to. And when it comes to writing to a brand new file, what you probably want to check is the appropriate mode. So let's go man3fopen. And let's go look at our modes. Oops. man3fopen. Here we go. So we have a bunch of different modes that we have for writing to a file. So there's W, and W on its own truncates a file to 0 length. So if we truncate a file so that it has a length of 0, what we're essentially doing is we're overwriting the file. We're overwriting the existing content of the file, and we're writing over it. Whereas if we were to use A would allow us to append to the file. So it takes the existing content, it keeps it all there, and then it positions your cursor at the end of the file so that you append onto the end of the file the next time that you write. So when you're copying a file over and the file already exists, you probably don't want to append to the existing file. You probably want to overwrite your existing file in that case. So in this case, I want to overwrite the existing file, so I'm going to use the W option over there. So fopen argv2. And we want to write to that brand new file, so I'm going to specify W. OK, so we've opened these two files. But let's say that the source file, for example, doesn't exist. Let's say I try to specify a source file that doesn't exist. And let's say that I try to write to that source file. So for example, I'm just going to use fputc, and I'm just going to write the letter H to a source file that doesn't exist. What's going to happen? So let's try use a source file that doesn't exist, and I don't know, there we go. We've got a segmentation fault. So I try to fopen a file that doesn't exist, and then I try to write to it. So there's two big things going wrong here. First of all, we try to write to a file that doesn't exist, so maybe I should use fgetc instead. Let's try use fgetc and see if we still have the same issue. So we open the file with the read mode, but we try to write to it, so that's our first issue. So let me see what happens if I try to read from a file that doesn't exist instead. Same sort of issue. When we try to read from a file that doesn't exist, we also get a segmentation fault. And typically speaking, when your program has a segmentation fault, it's because you're trying to access memory that you shouldn't. So maybe what we should now do is see what this source file actually is. Because we know that source file is a pointer to some struct that's internal to our program. So if I were to use printf and we print out that pointer, let's print out that pointer using printf. Oops, I can type. So once again, we're going to try open a file that doesn't exist and read from it. We can see that the pointer that's being printed out is nil. So usually when printf%p prints out nil, it's actually referring to a null pointer. So fopen will return a null pointer in the case that it fails for whatever reason. And we can double check that by going back to the man page for fopen. Man3fopen, and then let's go to the section on return values. Upon successful completion, fopen returns a file pointer, so it's a pointer to some internal struct that we don't really have access to. Otherwise, null is returned and errno is set to indicate the error. So we need to make sure that our fopen doesn't return null, because if fopen does return null, that indicates that some form of error has occurred, and we need to stop the execution of our program. So let's say we try to open the source file and it fails for whatever reason. We want to make sure that source file is not equal to null, because if it is equal to null, something's gone wrong. Again, when something goes wrong with your program, it's kind of like unhelpful for your user if you just crash from your program. So you probably want to print out some form of error message. And at the very end of last lecture, we talked about the p error function. So the p error function will go look at the error number that's been set by fopen and print out an appropriate error message. So now if we try that again, there we go. We get the name of the file that caused the issue. So in this case, this file caused the issue because it didn't exist. And p error has printed out an appropriate error message for us. So in the assignment that's coming out later today, you will be expected to do some error handling. And you will be expected to return, I think, 1 when something goes wrong with your program. However, we won't be testing the actual output of your errors. So as long as you print out an appropriate error message, it's fine. You don't need to match the error messages that the reference implementation produces, as long as you produce some form of appropriate error. And make sure that you write it to standard error. So standard error is, again, a special file that's already open for you in your program. OK. In fact, let's demonstrate writing to standard error. So let's say that I'm just going to make the assumption that if fopen fails, it's because the file doesn't exist. That's a bad assumption to make. But let's say that I want to write directly to standard error. Standard error is just another special file that's already open for you. So in order to write to standard error, we need to use fprintf. So regular printf, let's say no such file or directory. Regular printf writes to standard output. However, we want to write to standard error, which is a separate file. So I'm going to use fprintf. So with fprintf, I can specify what file stream I'm writing to. And in this case, I want to write to standard error, which has already been opened for us. And there we go, standard error. We can write no such file to standard error instead of standard output. And now if I compile and run this program, we can see that this output still shows up on our terminal. So you might be wondering, like, what's the difference between standard out and standard error? Because if I change this back to standard out and compile and run it again, we can see the output turning up in the same place. And that's because by default, both standard output and standard error get directed to your terminal. But let's say, for example, that I want to send my output to one place and I want to send my errors to another place. So let's say, for example, I want to print out a message to standard output. I want to print out a message to standard output. So let's say hello world. And let's say that I want to separate out the errors so that the errors of my program aren't in the same place as the actual output from the program. So let's say, for example, I want to redirect all of my errors to some form of log file. What I can do is send my error messages to standard error. And right now, if I compile and run this program again, we see that both the contents of standard output and standard error are redirected to the terminal. But what I can do is I can redirect just standard error. I can redirect just standard error by using this notation. So this 2 followed by a greater than sign takes the output of standard error and redirects it to a separate file. So let's say I redirect it to error.log. Error.log. We still get the contents of standard output showing up on our terminal, but now there's a brand new file called error.log, which contains any error messages. So this is really, really good if you need to keep a separate log of errors while also having some form of output from your program for a user to interact with. Similar thing, let's say that instead of redirecting errors, we just want to redirect standard output. What we can do is use the greater than sign without a number. And what that's going to do is it's going to take out standard output. Sorry, it's going to take standard output from the program and then redirect it to some file. So let's redirect this to hello. So now we get the error messages showing up on the terminal because standard error hasn't been redirected. But we get standard output being redirected to, I think, this hello file. There we go. So that's just something to be aware of. Both standard output and standard error will show up in your terminal, but they can be redirected to point to different places. And if you wanted to, you could redirect both of them in the same command. So let's say I want to redirect both standard output and standard error. I could do both of those at once as well. OK. So we've talked about the difference between standard output and standard error. So let's go back to using p error. I believe p error also writes to standard error for you. So if you use p error in the assignment, that's going to write to standard error. So you should pass the auto test by using p error as well. So p error v1. Now, same sort of thing with the destination file. Let's say that something goes wrong with trying to open the destination file. You also want to print out an error message. So what I'm going to do is I'll just copy this code, adjust it to deal with the destination file, and the destination file was specified in argv2. All right, so we've successfully opened both of our files using C library calls. So the next thing that we need to do is actually copy the content of the file over. So there's a couple of different ways that we could go about doing this. We could just read each byte from the original file one by one and then write it to the brand new file. So I could say, take our destination file and read a character from it in a loop. How do we go about doing that? Well, we know that we can read bytes from a file by using fgetc. So what I'm going to do is I'm going to use fgetc, and I'm going to specify where I want to read from. So I probably want to read from the source file. And we can see that fgetc returns an integer. So let's go see what fgetc returns. Man3 fgetc, and we'll look at the return value. Return. fgetc reads the character read as an unsigned char casted to an int. So fgetc will read in a character and return that character if it successfully reads it in. Or it returns EOF on end of file or error. So what we want to do is we want to keep reading from the file over and over and over again until we hit the end of the file. So we can use a loop to do that. While fgetc from our source file is not equal to EOF, we want to keep reading. But this is kind of meaningless to us because we're reading in a byte from a file, but we're not actually doing anything with that byte. So when we read in that byte, we also want to assign it to a variable so that we can make use of that byte. So I'm going to say while c is equal to fgetc. What that's going to do is it's going to read in a byte from the file. It's going to assign it to the c variable. And then since this expression also just happens to return, since expressions like this also return the value of the left-hand side variable, we can compare the left-hand side variable against EOF. So we'll keep looping until we hit EOF, and every time we read in a character, we will store that character inside C. So now that we've read in a character from the source file, we can write it out using fputc to the destination file. And the destination file is there. OK, so we've read in a character. We've checked that we haven't reached the end of the file. We write that character out, and then we go on to the next character using this loop. So last sort of step here is once you've finished up with both of your files, you want to make sure that you use fclose. So fclose does a bunch of things. One of the last things that it does is it uses the closed system call that we talked about during the last lecture. So fclose is really just a wrapper around the closed system call. So we want to close source file. We want to close destination file. But it also does a few other things. So we talked about how fopen returns a special struct that's kind of internal to the C library. So we don't really know what's inside that struct, and we shouldn't ever be interacting with the content of that struct. But it allocates some memory for a struct. So since fopen is allocating memory, it's using malloc behind the scenes. And since it's using malloc, once we're done with that struct, we need to somehow free that struct. And that's what fclose does. Fclose frees the struct behind the file star. it frees the struct because we don't want any memory leaks. So every fopen needs to have an equal and opposite fclose. Let's remove that. There's also some other stuff that fclose does. Let's talk about that other stuff actually. Okay, so we talked about how the C library functions like fopen and fclose are wrappers around some of the system calls that we talk about, but they do a little bit more. So I said that fopen kind of allocates a struct, some form of internal struct, and that internal struct also contains a big array. Now, why does fopen allocate a struct containing a big array? In this case, the array is usually 4096 bytes. Well, it's to do with performance. Because let's say that I want to keep reading bytes from a file. Every time that I try to read some bytes from a file, I need to make a system call. And it turns out that the process of making a system call takes a bit of time. It costs a bit of performance for your program to stop executing and then transfer control to the operating system, wait for the operating system to do its thing, and then return back to your program. So instead of making a system call every time that we use, for example, every time that we use fgetC in this example, instead of making a system call each time, what's actually happening behind the scenes is when we open a file and we read from it the first time we actually use fgetC, for example, instead of reading 1 byte at a time, what fgetC is going to do is it's going to read in this case, 4096 bytes. And it's going to store those 4096 bytes inside our special internal struct. So it's going to store those 4096 bytes inside an array, which the file star kind of points to. And this means that the next time you use fgetC, we don't have to go ahead and make a request to the operating system again. We don't have to transfer control to the operating system, because instead of reading in just 1 byte, we read in 4096 bytes earlier. And those 4096 bytes have been stored inside an array. So this file star struct contains a couple of things. It doesn't just contain the file descriptor, which is behind the scenes. It also contains a buffer. And that buffer is going to, every time we use fgetC, I've mixed up my words. Let's do this again. So when we use fgetC, we're not just reading in 1 byte necessarily. We might be reading in 4096 bytes. And we do this for efficiency because making system calls over and over and over again takes up time. So by reading in 4096 bytes at once, the next time that we go ahead and we try to use fgetC, instead of having to make a system call, it can go ahead and use the remaining 4095 bytes in the buffer. So buffering is essentially a mechanism that we have to avoid making system calls over and over again. We can use buffering every time we read. We can also use buffering for writes. So let's say that I'm trying to write to a file. And I'm trying to write bytes to a file. So for example, in this case, I'm writing bytes 1 by 1 to a file. So the naive solution here would be for us to just use a write system call every time that we want to write a byte to a file. But we know that system calls take up time. System calls cost performance. So instead of writing a byte directly to a file each time, what fputC is actually doing is it's writing to this buffer. It's writing to this array that we have available behind the scenes. And when the array fills up, once the array fills up all of its 4096 bytes, it's then going to flush the buffer to the file. So it's going to take the 4096 bytes that have kind of filled up this array, and then flush that buffer to your file. So someone's asked, what happens if we use all 4096 bytes in the buffer? So once your buffer is filled up and we've exhausted the buffer, we flush that buffer out to the file. Now, maybe this is a excuse for us to do another example. I'm going to see if this works. It should work. Let's have a main function. And before my main function, I'm just going to print out some message. Let's say hello world. And then let's have an infinite loop. While true, let's just have an infinite loop there and then return. So, whoops, we'll call this buffering.c. Okay, so theoretically speaking, this program should print out hello world and then be stuck on an infinite loop. But if I go ahead and compile this program, we can see that our program's like stuck on an infinite loop, but it hasn't actually printed out anything. To standard output, despite us printing out before the infinite loop. Does anyone want to take a guess as to what's happened here and why our program hasn't actually printed out to the terminal? Why haven't we like immediately written out to the terminal? What might be delaying it? So what we've just written is in the buffer at the moment. It hasn't actually been flushed out to the file. It hasn't actually been flushed out to standard output. So it turns out that whenever you try to write a new line to a buffer, whenever you write a new line character, it turns out that even though the buffer isn't filled up, standard I/O will essentially flush the buffer for you. So because I didn't have a new line, the contents of the buffer weren't flushed to the file. But if I add in a new line, we can see that the contents of the buffer have been flushed out. So if you ever need to flush a buffer, a very quick and easy solution to do that is just to print out a new line character. But there is one other way that we can force a buffer to be flushed without using a new line. And that's by using flush. Flush. Here we go. Flush flushes a stream. For output streams, flush forces a write of all buffered data for the given output stream via the write system call. For input streams, flush discards any buffered data. Okay, so I've written some stuff using printf. That stuff is stuck inside the buffer, so I want to flush the buffer out. So I'll say flush, and in this case, I want to flush out to standard output. And now we can see that, now we can see hello world being printed out, and we can see that there's no new line because we haven't printed out a new line. So that's just something to keep in mind. So now that we've talked about buffering, we can talk about the last thing that fclose does, and that is fclose will flush out the buffer. So even if you don't have 4096 bytes, even if you haven't like filled up your buffer, fclose will make sure that your buffer is flushed for you before your program exits. Normally speaking, if your program exits successfully, it should flush all of your buffers. But let's say that you've run into some sort of error that's caused your program to crash, and you want to make sure that you've written to your files before the program actually crashes. What you can do is you can add something to handle crashes. We don't talk about signals anymore in this course. But essentially, there are ways to detect whether your program's like hit a segmentation fault, and you can use that to flush your buffers before your program terminates. OK, so fclose does three things. First of all, it flushes the contents of any buffers. It frees up any allocated memory behind the scenes. Sorry, it closes the file using the close write system call, and then it frees up any memory allocated behind the scenes. Why should we flush the buffers? If we fail to flush out buffers before the program exits, that means that whatever is inside that buffer isn't going to actually be written out to the file. Because again, contents normally only get flushed out from the buffer to the actual file, A, when the buffer fills up, or B, if we print out a new line. But if you're ever in a situation where you haven't done one of those two things, you want to make sure that the contents of the buffer are flushed out from memory to the file before your program terminates. What was that, sorry? So the thing with like the hello world program, let's see if I can find that example again. The thing is, usually when you interact with a file, typically speaking, when you print out hello world, like in the past, you've printed a new line at the end. And printing out new lines kind of forces out that buffer to be emptied. This is what we call line buffering. So line buffering essentially says that when we write a new line to the buffer gets flushed. So the reason why previously, let's say that I did this without a new line, And let's say that I do this without an infinite loop and without using flush. If I run this program, we can see that like we didn't print out a new line, but the contents are still printed out, right? And that's because when your program terminates, it's going to make sure to flush out all of your buffers for you. So when a program exits normally, it's going to flush out your buffers, which means that you don't need to manually flush. But if you have an infinite loop, right? If I have an infinite loop, that infinite loop is going to mean that the program never actually properly ends, right? So in that particular case, I need to use an flush. I need to use an flush to make sure that the contents get flushed out from the buffer to standard output manually. So typically speaking, you will never actually have to use flush unless you're doing some wacky error handling sort of thing.
So what happens if we don't use flush?
What happens if I don't use flush here? So let's say I exclude the flush. And I think I demonstrated this earlier, but I'll run it again for you. There we go. So we're stuck in this infinite loop. This stuff has been written out to the buffer, but it hasn't actually been written out using a write system call from memory, so from the buffer to standard output. So since the stuff's like stuck in the buffer and it hasn't actually been written to the file, we don't see that output being produced on our terminal. Yep. What's that? Sorry? Yeah. So if I added a scanf right after, so let's say print enter input, scanf will also flush the buffer. So let's say that I read in an integer, %d, so yeah, trying to use a read syscall while you've got some stuff in the buffer will also force your buffer to be emptied. There we go. So that also works. That's another way to go around buffering. Yep. So, as in, you want to like, you don't want to like flush? Is that what you're sort of saying?
Like specifically empty it, so like if I decided to flush it, I wouldn't be able to get the print out.
So you want to like empty out the buffer. Yeah. I don't think this is like typically behavior that we want because it could lead to undefined behavior in different systems depending on their buffer size. So typically speaking, you don't want to like totally empty the buffer. Actually, the one case that I could see where it might be handy to flush your buffer is, let's say that you've like read from a file and then you know that the contents of that file have changed somewhere else. You want to make sure that your buffer's like sort of up to date. So if you use flush, for an input stream, what it does is it discards anything that's already been read into the buffer and it forces it to use a read system call again. All right, does that answer your questions about buffering?
Yeah.
Cool. OK. Yeah, so let's see what happens with so yeah, this is just a worked example of what might happen with buffering. So let's see, fgetc is going to, instead of just requesting 1 byte, it's going to request 4096 bytes using a read system call. And now the next 4095 times that we use fgetc, instead of making a system call, it is going to go ahead and it's going to use the 4095 bytes that we've already read in. And that keeps happening until we exhaust the buffer. Lovely. OK. So there is one last system call that we need to talk about when it comes to files, and that is seeking. So back during our last lecture, we talked about how when we open a file, we create an entry into the file descriptor table. And that file descriptor essentially keeps track of two things. First of all, it keeps track of which file you've opened. And secondly, it also keeps track of where you're up to inside that file. So how far into the file you currently are. So that's what we kind of call the cursor. The cursor keeps track of like where you are relative to the start of the file. But there might be circumstances where you want to move the cursor around manually. Let's say that instead of reading from the start of the file, you only want to read the last byte of a given file. So let's try write a program that only prints out the last byte of a given file. Let's do this here. Oops. Let's call this last byte.c. Oops. and get rid of that. All right, so once again, need standard.io.h. Probably would have taken a command line argument to figure out what file to read from. argv. All right, so every time that you rely on command line arguments, you need to make sure that the command line argument has actually been supplied. So we'll check if argc is equal to 2. If argc is not equal to 2, we have a problem. So we'll say printf usage oops, need to quote that. There we go. So we want to print out the last byte of the file. Yep. argv1. So argv0 always contains the name of the program. So what's really convenient about using argv0 instead of saying usage last byte, let's say I did this, for example, instead of having argv0. Let's say I did this, last byte.c -o last byte. OK, so let's say I run the program without giving it an argument. It prints out the right thing. But let's say that instead of using the last byte program from the current directory, I go to a different directory. And I want to use the program this way. 23t, actually no, even simpler. Let's go back to here. cd 23t2 like 10. Let me just rename the program to something else. So I'm going to rename the program from last byte to, I don't know, blah. OK, let's run the program again without giving the right amount of arguments. We can see that the error message still says last byte instead of blah. So I've kind of like hard-coded the name of the program into my error message, which is kind of bad in the case that I like rename the program or I move the program to somewhere else and I use a different path to invoke the program. So what I want to do instead is rely on argv0, because we know that argv0 will always contain the name of the program. So I'm going to replace this with a %s. And then I'm going to use argv0 so that it always uses the name of the program regardless of what we've called it. Does that make sense? Yep. OK. So we've checked whether we've got the right amount of arguments. We don't want that. Disable. All right. So I want to print out the last byte of a file. So there's a couple of ways that I could go about doing this. What I could do is I could just like try read the entire file using a loop until I get to the last byte. So we'll say int current byte, int last byte. And what we're going to do is while current byte is not equal to EOF, whoops. Sorry, while current byte is equal to fgetc, let's just say that we want to read in from the file. Well, in order to read from a file, we need to open that file. So let's open up the file. We'll call this stream is equal to fopen argv1. And we want to read the file to get its last byte. Once again, every time you use fopen, you want to make sure that nothing went wrong with fopen. There we go. Yep. Oh yeah, we should have a return one. That's a good point. Yeah. There we go. All right, so I'm going to read in a byte from the file. There we go, and we want to read in from stream. I'm going to keep reading in until I hit EOF. And every time I read in, I'm going to set last byte to be equal to the current byte. There we go. So what it's going to do is it's going to keep reading in new characters until it hits EOF. Once it hits EOF, it's going to end the loop. So last byte will still contain the final byte of the file before the EOF, because we never enter the loop if it is equal to EOF. Now, what I'm going to do is I'm just going to print out the last byte of the file. So we'll use putchar last byte. And this should theoretically print out the last byte of our file, which is totally fine. And we can test it. Let's choose a random file. Let's look at, well, actually, let me just make a new file. Let's make the last character H. And let's write this to some file. Let's just call it blah again, because I'm very creative. OK, so let's compile and run our program. This should, in theory, just print out the last byte of that file. Cool, so we can see that the last byte is a H. Let me just go change this to print a new line once it's done. Putchar new line. There we go. All right, so we can see that the last byte of that file is a H. Let's try a longer file and make sure it still works. Hello world. We can see that the last byte of that file is an exclamation mark. But that's really, really inefficient. But let's say that I have a file that's maybe gigabytes or terabytes long. In that sort of case, if I had a file that was gigabytes or terabytes long, if I had a massive file, this loop would have to read in every single file of that, every single byte of that massive file. And that might take a while if your file's like terabytes long. So it's sort of inefficient to read every single byte of a file just to get to the last byte. So this is where our final system call comes in. We have one last system call called lseek. lseek. lseek repositions the file offset of the open file descriptor to whatever offset that we specify. So for example, let's say that I want to jump to the end of the file. What I can do is I can use lseek so that instead of reading from the start of the file, I position the cursor to be at the very last byte of the file, for example. Now there's three sorts of ways that we can use lseek. We can use lseek to manipulate the cursor relative to where it currently is. So let's say, for example, our cursor is currently up to the 5th byte of the file. We've already read in 5 bytes. And now we want to skip to 10 bytes after that. So we want to skip to the 15th byte. What I can do is I can use seek current. And what seek current is going to do is it's going to move the cursor relative to where we are. We have seek set. And seek set is going to be relative to the start of the file. So let's say I've already read in 10 bytes, but I want to go to the 1000th byte of the file. Then I can use seek set and ask seek set to take me to the 1000th byte of the file. And finally, there's seek end. And seek end is going to be relative to the end of the file. So if I want to read the last byte of the file, what I can do is I can use seek end and use seek end to place the cursor 1 byte from the end of the file. So now, instead of having this loop, which loops through and reads the entire file, which is going to be inefficient, what I can do instead is use lseek. But one thing to note with lseek is a system call. Oops, that's the wrong man page. lseek is a system call, and the system call expects a file descriptor. We typically don't want to work directly with system calls. We want to work with C library functions. So what we can use instead is fseek. Fseek is a wrapper around lseek, and instead of taking a file descriptor, it will take the result of fopen, so a file stream, and it performs the same sort of thing. So once again, we have 3 different options. We have seek set, seek current, or seek end, which is going to be relative to the start of the file, where you currently are in the file, or the end of the file. So I'm going to use fseek on the file that I've just opened. Last byte. Oops, is that the wrong place? There we go. I'm going to use lseek. Fseek. We'll specify the file, which is file stream. We will specify our, whoops, what else do we need to specify? We will specify the offset. So we want to read the last byte of the file. So it's going to be -1 bytes from the end of the file. So I'm going to say -1 from the end of the file. And what this is going to do is it's going to move the cursor to the very last byte of the file, so 1 byte before the end. And now the next time that I use fgetc, the next time I use fgetc, it's going to give me the last byte of the file. Fgetc stream. There we go. Whoops. Yep. Let me just check that. Hang on. Oh, wait, I'm so silly. There we go. There we go. So the last byte of that file was an exclamation mark. So we get an exclamation mark. Perfect. All right, so I think that's a good point to have a break. After the break, we will talk more about file systems and the different types of file system objects that you might have, like files, directories, etc. So we'll come back in 5 minutes. Do you think I missed anything in terms of I think that got everything. Yeah, I don't think directories will be happening too, but that's fine. We'll video tomorrow. It's just subset 5. Yeah. So Leonard says the first 2 stages to the floor.
Yeah. I do agree that it's like,
I'm not too concerned as long as we just scale those first 2.
yeah, that's what I was suggesting that we, that we scale.
Do Jasper, you're saying?
I don't
Do it not Jasper.
Oh yeah, I'll send
I
it.
mean, he's right there.
Oh,
He's being there all the time.
Index.
Yeah, that's going to be line of operate implementation tutorials. Probably just end up sitting in the lab. Hello. Just log files. I think we're just both very tired from busy weeks and assignment writing.
Oh, really?
Xavier's been doing most of the assignment stuff.
Did you put it up?
Yes, we'll have it later. So the specification is a fully complete, so when it's working like partially way. Hopefully pushing the specification. Of course, I'll let you set that.
What would you reckon what is next?
What's left to do after farm?
As in like left to do this lecture or like after this lecture. So Dylan's doing Unicode on Thursday. Talk about processes next month.
A lot of times we talk about processes.
Yeah, so that gives us 4 weeks. I think processes might be a single workshop. So that means we can go to friends on Thursday.
But we've been pretty
Yeah, we've like spent I've got a lot of time to do it, so maybe this means we can actually talk about virtual memory.
Oh, what a bit network.
Modify the course outline slightly and throw it in. I think we can do it at the end of the week, essentially. Non-assessed content.
What do you mean?
Yes, you could. 3 minutes.
maybe just nudge the mouse a bit so it doesn't.
I've realised that me driving home after like doing like writing these assignments back like early 10 given times is not a good idea.
So I just like pull stuff so I can not flex it as a foot drop. This is why I can leave now. Just keep it below my I would rather like sleep on the ground for 2 hours than try slightly sleep on the road.
Yeah.
Be good most likely. Matrix reached out to us about looks like you're running out of Discord. Yes, I am aware.
What's the typical? What do you usually play?
So what I usually do is I just like first of all just run half mode and then use like what's it called? Dust to see what second space is. It was 20 gigs at the end of last time, I'm pretty sure. I don't know how it's 45.
Like that's
You know what? I'm gonna check now. So remove anything that's like obviously taking up space and doesn't need to really be there. Then what I'll do is I'll go to like password directories and harden the compression. Oh wait, I realize Echo is still going to record this.
All right. So let's talk. Let's move on from talking more about like interacting with the contents of files. Let's talk about file systems and how different files are like stored and structured on our machines. So we have different types of storage devices. So we've talked about like solid state drives, we've talked about hard disk drives. You could have magnetic disks, which are kind of ancient technology, but they're still used quite a bit for long-term storage. So we've talked about how a file is really just a sequence of bytes. It doesn't have to be null terminated or anything. It's just a bunch of bytes stored somewhere. And bytes don't really directly have meaning. It depends on how we choose to interpret those bytes. So it depends on context. Now we probably want to structure our files in some sort of like, well, structure, right? Because it'd be pretty annoying if like all of your files were just in one folder. You'd probably have like tens of thousands and maybe even like millions of files all in just one place, right? So you want some sort of structure for your files. And if you've used a computer before, which I'm sure all of you have, you've probably stored files within folders. So a directory is really just what you've probably called folders in the past. It's an object that contains 0 or more other files or other directories. So directories can contain other directories, or they can contain, they can contain directories and other files. Now a file system keeps track of a couple of things. It kind of stores this directory structure, and it also maintains metadata. So metadata is other data about the file. So if you have a file, you might want to keep track of when it was last modified. You might want to keep track of what type of file it is. You might want to keep track of the size of that file so you know how long the file actually is. What else might you want to store? You might want to store permissions for the file. So let's say I have a file that contains some secrets. Sorry, I have a file that contains assignment solutions on CSE machines. I don't want all of you to be able to read the assignment solutions, right? So it's important that I have some notion of permissions to make sure that you can't read my files. OK, so that's the job of a file system. So when it comes to well, any operating system, typically speaking, files have names. Files have names, and file names can contain any byte except for these two special values. A file name cannot contain a null terminator, and a file name cannot contain a slash, because we use the slash to separate different components of a file name. So you can't have a null terminator in a file name. You can't have a slash in a file name. Everything else is allowed to be in a file. Most file systems also have a limit on how big a file name can be. Usually it's about 255 bytes, but it depends. There are also two special file names that you can't assign to a file, and that's dot and dot dot. And why is that? So I'm currently in a folder called 23T2-lecture10. Does anyone know what CD command I would use to go to the folder that's above it? So how could I go back to this lec folder? Yep. Yep, CD dot dot takes me up to that directory's parent. So we can use dot dot to traverse this directory tree and go up towards the top directory. So if I go CD dot dot, that takes me to my home directory. If I go CD dot dot again, where am I now? I am in /home. Now I can go CD dot dot, and that's going to take me to the very root of our directory tree. So the slash directory is what we call the root of the directory tree. It lives at the very top of the structure. If I go CD dot dot again, it's not going to take me anywhere since we've reached the top of that directory tree. Yep. Just CD dot 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 do anything like this. So dot 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 does not have any special meaning. You could just make a file called dot 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 if you wanted. So the reason dot and dot dot are special is because every directory comes with a dot and a dot dot entry. So if I go ls-a, ls, actually what is ls? Does anyone know what ls does? Yeah, so it lists the contents of a given directory. So ls is going to show me that all of these folders or files exist within the current directory. But it turns out that regular ls hides some files. In particular, it hides files that start with a dot. So if I go ls-a, Whoops. That didn't do anything. ls-la. Oh, it's because I'm using a different ls. Let me fix my ls. ls, there we go. ls-a, there we go. So we can see that every directory comes with two special entries. It comes with an entry for a dot, and it comes with another entry for dot dot. Dot dot will always take you to the parent directory, whereas if I use cd dot actually doesn't do anything. Cd dot just takes you back to the current directory. So the dot is kind of like a self-referential loop. It refers to the current directory. And if I go to, let's say, my home directory is going to have a bunch of files, but we can see that it also has a dot entry and a dot dot entry. Dot dot will always take you to the parent, and this dot on its own takes you to the current directory. So having a directory entry which just refers to the current directory might seem kind of useless, but it turns out that you've been using this directory entry a ton without realizing. So let's say I go back to here, cd lex 23t2 lec 10. We have a request from someone in chat to be quiet. Oh, yeah, so someone spotted it. Yes. So I have a bunch of different programs in this directory. I have a program called buffering, and I have a program called blah. What happens if I try to run buffering? It doesn't know where the buffering program lives. It turns out that when you run a program, let's say ls, well, where does this ls program actually live? Where does this ls program actually live? Because ls doesn't live in this current directory. So in week 9, we're going to talk about where your shell kind of looks for programs by default. But by default, your shell is looking for programs in a special location. And buffering lives in the current directory. It doesn't live in one of those special locations. So in order to tell our shell to use the buffering file from the current directory, what we can do is // // says access the file within our current directory called buffering. And that's why we've always placed a // before trying to attempt to execute a program. The // tells our shell to look for the file in the current directory.
If I were in the previous directory,
Yep. So you, /23t2 lec 10 /buffering also works. But even then, I don't actually need this // in front. So my shell sees that this is a path. It sees that it's a path to a file. And since it sees that it's a path to a file, it will try follow that path and execute the program. So we don't even need the dot in that particular case. Similarly, what I could do is I could go into a different folder. Let's say I go to 23t1. OK, so let's think about where we are in this directory tree. It'd be really good if I had a pen. Actually, no, let's just do this in chalk. It's kind of hard to see, isn't it? OK, you know what? Let's just do this over here. All right, so I'm currently in my 23t1 lecture folder. And let's say that I want to run a program inside my 23t2 lecture 10 folder. Well, what I can do is ... Where does ... take me? What folder would ... take me to? It would be the parent directory. And what's the parent directory in this case? The lec folder. OK. So ... is going to take me to the parent directory. Now, from the parent directory, I can say, OK, I want to go to 23t2 lec 10, right? Because relative to where I currently am, 23t2 lec 10 is up the parent directory and then back down. And then I can run the buffering program from this folder, because that's kind of the path to the buffering program from where I currently am. Yes? If you want to go back to the home folder, yeah, you could do this. And that also works as well. Does that answer your question? Or did you ask something else?
No, that answers my question.
OK, lovely. All right, also, it's getting kind of loud in here, and it's hard for people to hear, so please be quiet. Thank you. All right. So we have ... and ... And again, these are special directory entries that live in every directory and take you to either the current directory or the parent. Okay, so directories or folders are really just a list of other files and a list of other files and other directories that live within that directory. So yeah, files and directories can be accessed by constructing path names. So for example, my home directory has this path, /home/abram. Now there's two sorts of ways that we can classify path names. We can have an absolute path or we can have a relative path. So an absolute path always starts with a slash, and it gives you, and an absolute path is essentially the path to the file from the root directory. So for example, this path name can be broken down into 3 components. This first slash refers to my root directory. This refers to the home directory that's within my root directory. And this refers to the directory that's named after me within my home directory. So I can follow this along. So I go to my root directory. I can see that there's a directory called home, so I can go into that. And now I'm in /home, which is a folder within my root directory. And I can go into Abram, and that is my full path. That is the absolute path to where I currently am from the root directory. But we can also have relative paths. So we have this notion of a current working directory, and the current working directory is just where you currently are. So in a shell, for example, you can check what your current working directory is by using the pwd command. Pwd just stands for print working directory. So earlier on, I was in this folder. So, whoops, we need to go to lec, and then 2322 lec 10. Okay. Earlier on, I was in this folder. Okay, that corner over there is getting kind of loud. All right. So before I was in my home directory, and I used the cd command to get to my lecture 10 directory. And notice how I didn't have to type out all of this, right? I didn't have to type out all of this. I didn't have to type out an absolute path. All I had to type in was this section, lec/23t2-lec10. This is what we call a relative path. So this path that I've specified here is relative to my current working directory. So since I was here before, what it essentially did was that it took this directory and it kind of like added this path onto that directory. So it knew that I was here. It knew it was in my home directory, /home/abram. It looked for the lec directory relative to my current directory. It went into that directory and then looked for this directory relative to the lec directory. So it's kind of almost like a linked list in a sense. You're kind of like dereferencing each sort of like node, in this path in order to get to places. Well, it's not really a linked list because what it actually is a tree. It's a tree structure. So if you've done 2521, you might have seen trees before. And we can see that it's sort of a tree because it has a root at the very top. And each root has children. So for example, we can see that we have a bin directory here as a child of the root directory. And we can see that we can traverse down in order to get to other directories from the root. What else is there to note here? OK, there is an exception. There is something that makes the file system structure not exactly a tree. And that is what we call symbolic links, which we'll get to very, very shortly. Symbolic links are kind of like very similar to this concept of shortcuts, which you might have seen in Windows. Symbolic links are basically ways to get from one directory to another across the tree. So you can essentially add new lines in using symbolic links. And these symbolic links kind of make it a graph. What happens if you try to run a program without /? So if I go back to here and I try to run buffering, we can see that it fails to find where buffering lives. Yes? If I moved it to if I moved it to something in my path, then it would work. But we will talk more about that in week 9. OK. Actually, we'll probably talk more about it next week since we're getting up to processes very soon. All right. So yeah, your file system is sort of structured like a tree, and each node is either a directory or a file. There's other types of files which we'll get to very, very shortly, but each of these nodes is either a directory or a file. If it's a directory, then a directory can have children. So for example, the include directory down here has children, but files are always going to be leaf nodes. A file can't have children because the file can't contain other files. OK. Whoops, what happened there? Let's scroll back down. So we talked about PWD to print out your current working directory. You talked about relative path names. All right. Now let's talk about what files actually are on Linux, on Unix systems. Because we said that files are really just an array of bytes. And it turns out that you can actually represent a lot of things using just an array of bytes. So file systems on Unix represent a lot of things as files, even though they aren't actually files. So regular files are just treated as files on a file system. Directories are also treated as files. So it turns out that you can interact with directories by using the read system call and the write system call behind the scenes. There's storage devices, so you can directly interact with storage devices as if they're files. And in fact, I'm going to demonstrate this on my machine. Let's go to my root folder. Inside my root folder, there's a bunch of other folders. So for example, we can see there's home, where all the home directory lives. All the home directories live, sorry. We can see that there's another folder called dev. Does anyone want to guess what dev might stand for? Yeah, so the logical conclusion to come to would be, oh, it's probably just where you write your code, right? It's the development directory. But dev actually stands for device. CD dev contains a bunch of devices. So it turns out that when we communicate with a device, right? Let's say I've got a hard drive plugged into my laptop, for example. When we communicate with a device, all we're really doing is we're sending bytes to it, and we're receiving bytes from it. We can either send bytes, so write bytes to the device, or we can read bytes from the device. So read, write, that sounds really familiar, right? With files, we could also read from the file, or we could write to the file using the read and write system calls. So what Unix does, and Unix-like operating systems like Linux, what Unix-like operating systems do is they represent each of your devices as if they were just a file. It's kind of an abstraction that's been provided by the operating system that allows you to treat devices as if they're just files. Because again, you can just read and write to files, and that makes it very, very similar to a regular file. So in fact, if I run ls-l, which is also something that we're going to talk about, we can see a bunch of things about all of these different files. Actually, let's go to a normal directory first. ls-l is like the ls program. It lists out different files in a given directory, but it prints out some extra information about those files. So for example, this column over here tells me when the file was last modified. This column over here tells me the sizes of each of these files. So for example, I have a file over here that's 181 megabytes large. This column over here tells me who owns the file, so which user has ownership of the file. So one thing that you might notice here is that this over here is kind of repeated twice. So Unix and Unix-like operating systems, I don't think Mac OS does this actually, but a lot of Unix-like operating systems like Linux have the concept of what we call a group. And the idea of what a group is actually best demonstrated by going to the class account. What could possibly go wrong here? All right. So let's say that I am running COMP1521, and I've hired a bunch of tutors, right? When I have these tutors, I want these tutors to be able to access solutions, for example. So what I can do is I can set up what we call a group. So a group on a Unix system is essentially just a collection of different users. So what I'm going to do is I'm going to set up a group called CS1521, and I'm going to add all the CS1521 tutors to that group. Why is this really handy? Well, it turns out that when it comes to permissions, oh, I don't want to run ls here. That's probably a bad idea. OK. when I set up permissions, I can set up different permissions for the group which is associated with a file. So over here, we can see permissions for the file in this column. And we can see that there's an R permission, there's a W permission, and there's an X permission. Does anyone want to guess what R and W stand for? Read and write. So if you have the R permission, you're able to read a file. If you have the W permission, you're able to write to a file. Does anyone want to guess what X stands for? Execute. So execute allows you to actually run the file as if it were a program. So yeah, X lets you execute a file. OK, so what we can see is that there's 3 sets of permissions. There's one set of RWXs here, there's another set of RWXs over here, and finally there's one more set of RWXs over there. And each of these RWXs applies to a different set of people. So the first set of RWX is what we call the owner's permissions. So in this case, this RWX refers to the permissions that I have on this file. Now the second set of RWX is what we call the group permissions. And the group permissions apply to the group that's associated with this file. So in this particular case, this second column over here tells me what group is associated with the file. So in this particular case, I have a group that's also just named after me, and I'm the only person in this group. But on the 1521 class account, what I can do is I can have the CS1521 group, and I can add all the CS1521 tutors to that group. And what that means is, let's say that I have solutions to a lab. In fact, let's be very risky. Actually, would this be set up? I don't know. Let's say I have solutions to a lab. I'm going to go to here. What's a fun lab?
It won't async across.
It won't async across. Oh, you're
You
right.
can just show the private.
Like there.
Yeah, and you can show the.
Yeah.
Yeah.
OK. You're seeing a lot of secrets today. What's a weak one lab? Fibonacci. Fibonacci. There we go. So what do we have here? Oh, solutions are also just private here. Maybe this won't work. No. OK. This didn't behave as I expected, but let's analyze the permissions for this file. So according to this, let me just fix something very quickly. /bin/ls. There we go. According to this set of 3 here tells me that I, the owner of the file, so in this case the COMP1521 account, is able to read from the file, and it's also able to write to the file. But we can see that we don't have permissions to execute this file. And that sort of makes sense, right? Because this is a C file, and you can't just execute a C file. You have to compile it first. So for that reason, we haven't given ourselves execute permissions. This second set of 3 dashes applies to the group that's associated with the file. So in this case, the CS1521 group, which happens to have the same name as the CS1521 user, has no permissions on this file. So all the 1521 tutors, which I've added to this group, don't actually have any permissions on this file. They can't read it, they can't write to it, they can't execute. And then we have the final group of 3. This is what I like to call the public group or the other group. So these permissions apply to everyone else. So these permissions would apply to you. Because you aren't COMP1521 tutors, you won't be in the CS1521 group. So these permissions say that you don't have the ability to read the solutions, which is probably a good thing, and you don't have the ability to edit or execute the files either. All right, so we have the idea of permissions over here. We have the idea of the user that owns the file. We have the idea of a group that's associated with the file. We have a file size, we have a modification time, and we have a file name. Now, there's one last thing to point out here, and that is the very first character over here, the very first letter. So you might notice that some files have a D in front of them, and other files have a dash. Does anyone want to guess what the D stands for? Directory. So if we look at the output of ls-l, and we see that it starts with a D, that tells us that the file is that the particular entry is a directory. If we have a dash, for example, over here, the dash tells us that the file is just a regular file. So typically speaking, in this course, you'll only be interacting with regular files and directories, but there are other types of files, or well, fake files that are worth being aware of. And one of those examples is in /dev, cd/dev. In /dev, if I run ls-l, we can see that instead of starting with a dash or a D, we have a bunch of different files that start with a C. And C actually stands for what we call a character device. So a character device is essentially a fake file which allows us to interact with some sort of real physical device. So for example, there is one called, let's see, do I have it over here? /disk. Sorry, disk. Okay, here we go. By ID, no. Okay, this is a bit messy, but we should be able to go back here. Okay, I found it. NVMe. Does anyone know what NVMe is? Yeah, so NVMe is kind of like the standard that's used for like solid state drives to communicate with a computer. So it's sort of like the hardware standard for solid state drives. So NVMe 0 lets me directly communicate with my solid state drive on my laptop. So what I could do is, theoretically, if I wanted to just start writing random bytes to my solid state drive, which would be a really, really bad idea because I'd be like writing bytes to the middle of nowhere. But if I felt like just like writing bytes to my solid state drive, I could just send bytes to NVMe 0. Probably not a good idea. There is also, I think, one for CPU, CD CPU. All right, so there are a bunch of devices in here. Let's say over here. And what I can actually do with this device, MSR, I believe I can just straight up start writing CPU instructions to this device, and my CPU would just start executing them. So there are a lot of random things in /dev which allow you to like directly interact with the devices. Generally speaking, it's a bad idea to be doing it, but it is possible. So not every file on your file system is actually a real file. Yeah.
Does NVMe 0, does that allow you to wipe bytes as well?
Yeah, so I could like theoretically just like completely destroy my drive if I wanted to. I'm sure there'd be some like at some point I'd like destroy my operating system, so it probably wouldn't work. But theoretically speaking, it's possible. Yeah, so there's a lot of special stuff in here. Now let's do an interesting demo. I'm going to SSH into a CSC machine. And let's talk about what a terminal really is. So this window over here is what we know to be called a terminal. We call it a terminal, but it's actually short for terminal emulator. Why is it short for terminal emulator? Well, back before like we used like displays to interact with computers, we had literal physical devices called teletext typewriters. Teletypewriters. Teletypewriter. Let's see if I can find an image of a teletypewriter. So this thing over here is like a literal physical terminal. It's what we call a teletypewriter. In this particular case, I think it's used for deaf people, but teletypewriters are essentially a physical device where you can like feed an input and it can give you output. And a terminal emulator tries to emulate the behavior of a teletypewriter. It's a place where you can like enter an input. You can enter an input, you can send an input, and then you can get output back. So a terminal emulator emulates a teletypewriter. And if I go to /dev, there are, let's do this again. There are a bunch of files here called TTY0, TTY1, TTY, etc. So the TTY here actually just stands for teletypewriter. So it turns out that each of my terminal windows is emulating one of these teletypewriter devices. Also, I need to quickly check. Oh, this isn't going to work. So what you might notice is that I'm SSH into two separate machines, but let's make sure that I'm SSH onto the same machine, VX7. This might take a moment. Okay, so I now have two separate terminal emulators connected to the same machine. And inside my terminal emulator, there is a program running which takes the input I feed in and then spits out output. And that program is called the shell. So typically speaking, the shell that you're using is probably bash or ZSH. But there is a program that sits between your teletypewriter, that sits within your teletypewriter or within your terminal emulator called a shell. And it's responsible for taking input, calling other programs, and producing output. Okay, so I have two teletypewriters, two terminal emulators, and these terminal emulators emulate a teletypewriter. So it turns out that each of these teletypewriters, since it's emulating a device, it has an entry in /dev. If I run a command called tty, it tells me what this device is called, or where this device is located. So I can see that this terminal is hooked up to a file called /dev/pts/45, which we can find out more about. /dev/pts/45. It's emulating a device, and this terminal is hooked up to a file called /dev/pts/81. Okay, so these are really just files. And I could try write to these files. So let's say that I have my terminal on the left, and I want to send a message to my terminal on the right. Well, we know that there's a command called echo, and what the echo command does is it takes in an input and then it spits it out to standard output. But I can redirect the output of a program. We saw that we can redirect the output of a program by using the greater than symbol and then sending it to another file. So let's say I want to send this to hello. I can redirect it to hello, a file called hello in my current directory. But what if instead of redirecting it to another regular file, I redirect it to this terminal special file? So I'll say cat hello, echo hello, and I'm going to send it to the special file. We can see that the message got sent from this terminal to that terminal. Why is that? It's because the terminal on the right is hooked up to this device, /dev/pts/81. And by sending bytes to that device, the bytes that I send to that device get written out to this terminal emulator screen. So now let's say that you hypothetically were to SSH into VX07. You would also have your own teletypewriter. In fact, let's go to cd/devs/pts. We can see that a bunch of people in here have their own teletypewriter file. So for example, I can see there's me. Here's a bunch of other people's ZIDs. Let's send a message to this person's terminal. What could possibly go wrong here? Hello, I have hacked your machine. Let's just see what this person, actually let's take this person. They have /dev/pts/84. Now, I want you to look at this. What do you expect is going to happen? Do you think they're going to receive a message? Exactly. So ls-l, actually let's go /bin/ls-l. We can see that the owner of the file is this user. We can see that the group that's associated with the file is tty, and I'm not in that group. But essentially, the owner of the file has read and write permissions for their own tty. The group might have write permissions, but I'm not part of that group. And everyone else has no permissions on this terminal. So if I try to actually send that message, go, hello, I have hacked your machine to this person's sudo terminal, we can see that we don't actually have permissions to do that, unfortunately. There was a bug like 2 years ago which made it possible to send messages to anyone else, like other people's terminals. Thankfully, that's been patched. Actually, as one final experiment, just because we're like reaching the end of this lecture, and I don't think we'll actually get through more content. Should we do this now? Actually, we'll come back to this, but the main thing to note is that there's different types of objects on file systems. So you can have files, you can have directories, you can have devices which are represented as files. I guess the last thing that I'll cover is the idea of a symbolic link. Symbolic links. So let's say that I'm sick of having to say cd lec/23t2-lec10 each time. That's a lot of effort. What if I just had some form of shortcut to this directory from my home directory? What I can do is I can create what we call a symbolic link. And a symbolic link is essentially just a portal from one place in a file system to another. So I'll go to my home directory, and I'm going to make a new symbolic link by using ln-s. So man-ln, man-ln allows me to make links between files. So ln-s creates what we call a symbolic link, ln-s. And I want to make a symbolic link to the lec/23t2-lec10 directory. And I'm just going to call my symbolic link, let's just call it portal, because it's kind of a portal. Now, if I run ls-l now, we can see that our portal takes us to lec/23t2-lec10. So over here, we can see that the file type is L, and the L is short for symbolic link. And the symbolic link essentially just acts as a quick way to get between different parts of your file system. In fact, if I go to my root directory, we can see that there are a bunch of symbolic links already. So for example, this bin directory isn't actually a directory in my root. It's a symbolic link to another directory. So you can have symbolic links between files. You can have symbolic links between directories. Symbolic links can point to any other type of file system object. So we will see the implications of symbolic links in, I don't think we'll be in the next lecture. What we're probably going to do is we're going to pre-record an extra lecture just to make sure that you have all the content that you need for the assignment in time for the assignment. So I think in the next 2 days, I will probably upload one more video talking about file systems and stat. And that's going to talk about how to interact with, how you actually interact with the file system and get information like permissions, how you change permissions of a file, etc. So in the final 2 minutes, let's try a bit of an experiment. And this is going to be a quick teaser on how we deal with file permissions. Can you guess what I'm about to do? All right, so we know that my sudo terminal here is /dev/pts/45. You see where this is going, right? And if I use ls-l, actually, let me just fix my ls. Alias ls, there we go. If I do ls-l, we can see that I'm the owner of the file, right? So that means that I should be, since I'm the owner of the file, I should be able to change the permissions of that file. So there is a special command called chmod. Chmod stands for change mode, and the mode of a file essentially contains the permissions of a file. So what I could do is I could theoretically adjust the permissions of the file so that everyone else has the ability to write to that file. So theoretically speaking, if you wanted to access this machine, you could say z530 vx05. Wow, Xavier's been quick. Yeah. So yeah, you could SSH into this machine using your ZID followed by, wait, this is vx7, my bad. There you go. You could SSH onto the same machine and then start writing messages to this file. Keep it appropriate. I'm trusting you. In fact, is it 10:55 yet? It's not 10:55 yet. Maybe I shouldn't display this until the lecture recording stops. Also, if you do actually send stuff that you're not supposed to send, everything is logged, so we can investigate. How many seconds do we have? 8 seconds, and then the recording stops.